Yeah.
Okay, well, let's get started. Okay, now, it's probably always a good idea to look at things from a different point of view, different perspective. I invite you all to seek your own refreshments as usual. Today's speaker is Cosmas Zachos of Argonne National Lab, and he is going to talk about some aspects of a subject which should be familiar to everyone, quantum mechanics, elementary quantum mechanics, but he'll discuss things from a novel point of view, at least novel for most people. I've known Cosmas for far too long, some 40 some years since graduate student days. I've suffered through his criticism and his editorial wrath on several joint papers. I will let you read more about his academic career and his CV, which is posted along with the information about the speaker. So on that note, Cosmas, I'll let you take it away.
Okay. Let me. Okay. So first, apologies to a fair number of people in the audience who've already heard this talk at their home institutions. It shouldn't be very different from what they heard a million years ago. Secondly, I shouldn't be giving this talk. Tom should be giving this talk. But since he hasn't for 20 years, the number of years this has been our hobby, I guess I should describe our hobby. Okay, so the Martians land in Miami and they invade Dr. Curtright's office in the middle of the night, and they see this graph. And of course, immediately they say, yeah, we're advanced people. It says double slit in phase space. That's obvious. There's a slit here and a slit there. And we understand what happens. Some type of particle goes through every slit at these 2 points, and you get some sort of a Gaussian distribution of the oomph that goes through the slits. And then they say, wait a minute, what's this stuff in the middle? Looks like interference. But interference takes waves. And what kind of waves do you have? Is this quantum mechanics? And it says, no, you can't have quantum mechanics in phase space. We all teach our students the first week of class that you either work in coordinate space or in momentum space. So there's something wrong here. What on earth is this? At which point they panic and they start running away and they leave me to inflict the truth on you. On our planet, this problem was solved in the 40s. What you just saw is a Wigner function, and it's a phase space quasi-probability distribution function. And it's quasi-probability because you saw it's got negative values at some point. And what does negative probability mean? If I have probability -5 balls in an urn, what does that mean? It waits for me to throw in 5 balls to get 0 probability of having any balls in there, or what? And we'll discuss this. Lots of physicists were scandalized about this in the 30s and 40s. But it turns out that on our planet, there is a complete autonomous formulation of quantum mechanics based in phase space, and it's ordinary phase space, not quantum phase space or nonsense, just ordinary phase space, except functions compose in a funny way. There's only one operator in this formulation, no more operators, but this operator does everything. It's the adjustable wrench that describes quantum mechanics in its greatest generality. Okay, there are three alternate autonomous formulations of quantum mechanics. The first one is the Hilbert Space formulation of the 20s. It's the gold medal in that race. And it was invented by the standard superheroes, and you teach it to your students, and you solve most of your problems in it, of course. The second one, the silver medal, is the path integrals, invented by Dirac and finished off by Feynman in the 30s and 40s. And you also teach it to your students because there are some problems that path integrals do much, much better than the gold medal formulation. And I'll talk about the bronze medal, the phase space distribution function of Wigner. So therefore, phase space quantization, which was initiated by Wigner, initiated by nobodies in the 30s all the way to the 60s. Wigner was a nobody because that's his first paper in English. He was a young assistant prof at Princeton. I guess he wasn't a nobody because he'd introduced group theory to quantum mechanics. But he wasn't the superhero we all know. Groenewold was a grad student in wartime Holland, hiding from the Nazis and dreaming of writing a thesis. So he conceived all that hiding in the polder, for those of you interested in the history. Moyal wasn't even a graduate student. He was working for a British de Havilland, a British aerospace company during World War II, supporting a family. And he was talking to Dirac on occasion and corresponding with him, and Dirac was discouraging him on every step. He was dreaming of getting Dirac's enthusiasm and recommendation, maybe a PhD, maybe an academic job. Baker was a graduate student, that was his thesis, and Fairley was a fresh postdoc at St. Andrews. So what you just saw was a function in phase space, and it is a bilinear of Schrödinger wave functions. It's actually an autocorrelation of Schrödinger wave functions. It's basically the same Schrödinger wave function and its complex conjugate separated by some distance, and their overlap, and then you Fourier transform over all distances of separation, and the conjugate variable you call P, and that's the Wigner function. It turns out, if you're sophisticated about these things, it turns out that it's a special representation of the density matrix in the Weyl correspondence. Don't worry about it, I'll get there. And it's very useful describing quantum transport or flows in phase space, in quantum optics, quantum chemistry, nuclear physics, and therefore the study of decoherence, how quantum distributions morph into classical distributions, Liouville distributions, as they interact with the environment. But since coordinates and momenta, as you know, are conjugate variables, they're Fourier conjugates, and time and frequency are such. You can also have Wigner functions in signal processing. So you can analyze voice signals of Russian submarine hatches opening up in the middle of the ocean and stuff like that. And the mathematical structure of it, which I'll try to give you a glimpse of, is actually very nice. It has several applications in the structure of Lie algebras, M theory, and so on. None of that here. Okay, so I wrote the Wigner function before. I'm rewriting it. It has several kind of obvious properties. First of all, it's normalized. If you integrate it over phase space, it does what distributions of phase space would do. It normalizes to 1. It's a probability 1. Your particle is certain to be someplace in phase space. How do you see that? You see that by doing the p integral first. It gives you a delta function in y. You collapse the delta function in y, and you get the bilinear of the Schrödinger wave function. That's the probability distribution in coordinate space. And of course, it's normalized because Schrödinger wave functions are normalized. It's also real. Check it. Now, unlike Liouville wave functions, the Wigner function has an amazing property. It's very, very different than things you've seen before. It's bounded above. So it cannot be a delta function. You cannot be a spike in phase space and be at an exact x and an exact p. You are bounded above and below by something inversely proportional to Planck's constant. So you can never be spiky, you can never be certain. You can never be at one point in phase space. And how do you see that? Well, it's kind of obvious. What you saw there is the dot product of two continuous vectors, this one and this one. Oops. And so the dot product of two vectors is, of course, smaller or equal than the product of the lengths of these two vectors. So the Cauchy inequality. And if you work it out, you find that the Wigner function is bounded above and below. So it's bounded in magnitude. Okay, this turns out to be significant, but you already saw the beautiful head, quantum mechanics rearing its beautiful head behind this. Okay, now, even though it's not a probability distribution, if you take its marginal densities, namely if you integrate over p, as we saw, you get a bona fide probability distribution in coordinate space. And trust me, if you did the Fourier transforms and you took the x coordinate for it, you got the probability density, a bona fide probability, positive semi-definite probability density in momentum space. So the two cannot condition on each other, the coordinates and the momenta. If you know where you are in coordinate space, you cannot specify your position in momentum space and vice versa. Now, F, as you already observed, can and most often does go negative. This is what Wigner discovered in 1932. And like a cool cat he was, he appreciated that this is actually not a bug, it's a feature. We'll see that. And it's a wonderful thing. It's a hallmark of quantum interference. The statistician collaborator of Moyal, and Moyal himself in the 40s investigated negative probabilities. And then Feynman tried to use it to eliminate divergences in quantum field theory. It didn't work out. And recently, in the last few decades, Bracken and Molloy have done very nice things about the negative probability chunks moving in one direction, implying the particle, the positive probability, backflowing in the opposite direction, and all kinds of neat things. It's actually very informative. So what happens to these negative areas? They hide through the uncertainty principle. Okay, I'll talk fast here. Don't worry, the argument has been written down, but here's the thing. If I took a Wigner function with its negative regions and I convolved it with a Gaussian of width, of size, it's in phase space, larger than h bar. So I have a Gaussian in phase space whose base, whose characteristic width is larger than h bar. If I convolve this with the Wigner function, what I find is a positive semi-definite function. This is a theorem. It's not obvious unless you think about taking a classical limit of the Wigner function and looking at your quantum object with rose-tinted glasses, with classical glasses. But in any case, it's a theorem. What you get is something that is nowhere negative. It's positive semi-definite, positive or zero. This was discovered by a Dutch applied mathematician and a philosopher subsequently, unbeknownst to her, at Stanford. Her name was Cartwright. I assume there's no relation. So that implies that all the negative areas in the Wigner function are small. Why? Because assume you had a large area of uninterrupted negative values of the Wigner function. So something that has a puddle of negative values of size 10h bar. What you do then is you take a Gaussian of size h bar or 2h bar or 3h bar, put it in the middle of the puddle, and then you'd know that the convolution had to be zero, and in that particular point, the overlap would zero. I'm sorry, the convolution would have to be positive, and the overlap would have to be positive, but I have a uniformly negative, huge 10h bar puddle of negative values with a positive definite Gaussian overlapping with it. And so therefore, whatever I have is actually, if I took the appropriate integral, is actually negative. But there's a theorem that tells me that this cannot be. So therefore, the only flaw in the argument is the assumption that negative areas can be large, can be as large as they want. They have to be small in phase space. But we know what prevents us in phase space for putting in a galvanometer and measuring them in small areas in phase space. Basically, you cannot peek into things in an area, in a phase space area, smaller than h bar over 2. That's the uncertainty principle. Now, not all functions in phase space can be Wigner functions, or at least Wigner functions of pure states, which is what we're talking about here. You can generalize this very easily to mixed states. Well, we saw that it has a very special form. The Wigner function has a very special form. It's the Fourier transform of something like this. So if we Fourier transform it back, we have the autocorrelation function of two functions that depend on light cone coordinates, right movers and left mover coordinates. You know what I'm talking about. There are two orthogonal linear combinations. And so if I take the logarithm of that, it's the sum of two functions of these light cone coordinates. So if I take the cross derivative of the sum, I get 0, because two derivatives, the derivative that lets you survive has a partner derivative that kills you. And so this is the condition. If somebody throws a phase space function at you, this is what you do. You take its Fourier transform like this, you take the cross derivative, and you find 0. And of course, from reality, the left and the right movers are supposed to be the same. So the left and the whatever, you know what I mean. So we decided that it's a quasi-probability distribution. What does that mean if it's negative and all that? it is a distribution function in phase space because it serves as the cockeyed measure in phase space to yield expectation values for phase space C number functions. Okay. Consider this again. Quantum mechanics is a theory of observables, of expectation values. In this formulation, we're in phase space. Our observables are going to be C number functions, functions of phase space, like the classical Hamiltonian for the oscillator, which we'll see. Things like that. These guys, you find the expectation values of these observables by taking classical integrals with respect to the Wigner function. So here it is. This is the essence of my talk. If you were asleep before, please wake up. After this transparency, you can go back to sleep. It hardly matters. Here's the story. Weyl in 1927 discovered a very interesting association rule between black C number functions, ordinary classical looking functions in phase space, and green operators. Basically, he took an appropriate delta function, collapse of an appropriate delta function that involved operators and classical variables like this. So this immediately tells you that this is a completely symmetric function in P's and X operators. He evaluates this integral by hook or crook. Don't ask how, there are clever ways to do it. And he gets an operator, and that operator is completely symmetric in the ordering of X's and P's. The exponential can be always understood as the power series expansion of the order groupings of operators like this. Okay, now there are clever ways. If somebody gives you an operator, you can use Heisenberg relations to order it in this Weyl ordering. But there's a much better way. We'll see it soon. And you take a matrix elements of this guy as given. You find A, you find the so-called Weyl symbol, you put it in this formula, and you get the Weyl order operator. That's completely equivalent. Unlike quantum field theory, this ordering does not compromise the operator. We're talking about operators that are equal to any ordering of them. Okay, the golden rule of phase space quantization is that the expectation values of operators in the gold formulation that you use your students can also be gotten by, take a look at this, the Weyl symbol, this classical looking kernel of the corresponding operator in quantum mechanics. So your observable is a C number function, and it's the expectation value of this symbol in phase space with the Wigner function serving as some sort of a cockeyed measure, some sort of a strange measure that gives you what you want. So there it is. And now what's the corresponding thing to the von Neumann equation for the evolution of the density matrix in the operator formulation? Well, how does the Wigner function evolve in time? It evolves through an equation that Moyal found. Actually, Wigner had it. And it's very much like Liouville's theorem in classical mechanics. The time derivative of the Liouville density is essentially the Poisson bracket of the classical Hamiltonian with the Liouville density. Here in quantum mechanics, we correct this by a little bit by writing this star commutator. Okay, this is the most important point of this formulation. It all hinges on this magical object. It's an operator, It was invented by Groenewold in his thesis, published in 1946. And what it is, it's the exponential of this operator, which you could identify in a second with the kernel for the Poisson bracket. If I put in two functions, one on the left and one on the right, basically this is the power series expansion of these operators. The leading guy in the expansion of this is 1, but 1 minus 1 is 0. So the leading term is h bar times stuff times the kernel, the Poisson bracket kernel of your left function and your right function. Here, the left function and the right function are the Weyl symbol Hamiltonian, a classical kernel type Hamiltonian, and the Wigner function. And then there are higher orders in h bar. There are corrections. So think of this guy called the Moyal bracket as the Poisson bracket corrected with h bar corrections. And it turns out that it's the essentially unique one parameter associated deformation of Poisson brackets. There's only one way to extend to quantization with these properties in this formulation. You could imagine you lived on a funny planet where Schrödinger and Heisenberg and Dirac had never been born, and instead their locals, who were Moyal and Groenewold and Wigner, developed quantum mechanics as some sort of a stretch of statistical mechanics, sort of the way Planck went experimentally. Okay, the golden relationship of this formulation is, that's why I said that this is the one transparency you ought to focus on, is that multiplication of operators in Hilbert space is tantamount, is isomorphic to star multiplication of Weyl symbols, of C-number functions. So if I have, you remember every operator corresponds uniquely to a Weyl symbol, but that object is a Weyl order operator. When you multiply two Weyl order operators, you don't get a Weyl order operator. You have to reorder it. When you do that, what you find is that the Weyl symbol, the classical kernel of this product, is actually the star product of the two component operators. Okay. So now let's look at, if you recall, well, when you teach quantum mechanics to your students, the way you solve the time-dependent Schrödinger equation is you look at the time-independent solutions of the solutions of the time-independent Schrödinger equation, and then you compose them in a Fourier transform with respect to the energy and time. So what are the time-independent solutions of Moyal's equation? Things that star commute with a Hamiltonian, but just about everything starts commute with a Hamiltonian if it's a star function of the Hamiltonian. It's an associative operator. It turns out that there's a further condition for Wigner functions, which was emphasized by Fairley as late as the early 1960s. And it's this Star-genvalue equation, namely the star product of the Hamiltonian is commutative in this sense, basically is the same as the star product of the Wigner function times the Hamiltonian. And it is equal to a number times the Wigner function. So this and that is a Star-gen function, an eigenfunction of the star product operator. And this energy is actually the very same energy of the corresponding time-independent Schrödinger eigenvalue equation for the corresponding Schrödinger wave function. This star product you can actually rewrite if you think of Lagrange's exponential shift operator. You can think of as shifting the arguments of the Hamiltonian with not numbers this time, but operators that act only on F and not on H. So there's no ambiguity in this object. This is called the Bopp shift from her professor Bopp. The interesting part in this is that not only the if you have this Star-genvalue equation, if you have not only the Star-genvalue equation obtains for an eigenvalue that's the energy of the Schrödinger problem, but vice versa. Namely, if you have a function that obeys this Star-genvalue equation, then you can rewrite necessarily your Wigner function can be written in that left-right factorizable form that I wrote before. Okay. Now this Star-genvalue equation is helpful in all kinds of games that you would play in functional analysis, in the gold formulation, in the Wigner, in the Hilbert Space formulation of quantum mechanics. For instance, take this Star-genvalue equation and dot it on the left with a different Star-gen function if you don't have any degeneracy. So this product you can resolve because the star is associative. Trust me, it can be proven easily. You can use this Star-genvalue equation to give you the energy Star-genvalue that corresponds to F. But you can use this grouping, this Star-genvalue equation to give you the energy that corresponds to the Wigner function G. And so you have this funny equation now. If there's no degeneracy and the two Star-gen values are different, you realize that Star-gen functions, Star-gen functions of different Star-gen values are star orthogonal. Now look at this. This is not an integral. This is at every point in phase space. So here you have two functions with positive and negative parts, we'll see that in a second, that know at every point in phase space, they know how to stay out of each other's way and to give you a star product 0. It's not an integral relation, it's a local relation. I'm not sure you appreciate how amazing it is. You take the two functions, you unzip them in the middle of their bellows, you re-zip them with the star product, and you get star orthogonality at every point in phase space. Okay, so now if you don't have degeneracy, you can also find that by multiplying on the left and on the right and using the star commutativity relation that I showed you before, you can also find that the star product of two of the same Wigner function is proportional to the Wigner function itself. If you're thinking Hilbert space and density matrices, this is like the idempotence of density matrices for pure states. So the Star-gen functions, the Wigner functions, start projecting to their space. Their star orthogonality relation is actually this. And the normalization actually matters because it tells you, it will show you something interesting. take two different Star-gen functions that correspond to different Star-gen values that are star orthogonal that we had before. Now, integrate this general phase space relation over the entire phase space. You can convince yourself that you can integrate this star product by parts. This is a special property of Wigner functions in this particular formulation. You can integrate all the left and right derivatives by parts, and you get a simple overlap integral. So this guy was 0, so the overlap of these two Star-gen functions is 0. Now, if these guys acted in the same regions of phase space, if they didn't live in special superselection sectors of phase space, each one of them, but imagine that there's an infinity of these guys because every Hamiltonian has an infinity of Star-gen functions. You'd have a very peculiar system that they live, so they clearly act in the same phase space, and we'll see that. We'll see an example of that. And the only way they manage to get 0 overlap is by having very cleverly placed negative regions in their support, so negative values for the Wigner functions, at selected places. And magically, they give you 0 overlap for the infinity of Star-gen functions that are both star orthogonal and bland integral orthogonal to each other, 0 overlaps. So unless we'll see that there's one Star-gen function that's positive semi-definite, the Gaussian, the ground state, and all the other ones, in order to be star orthogonal with it, have to have negative regions. So this is my point that Wigner realized early on that, oh boy, this is a feature. Negative areas of Wigner functions are a feature. They're not a liability. Okay, let me give you a quick illustration with the Star-genvalue equation of the fundamental relation. How do we get expectation values? What is the expectation value of the Hamiltonian? Well, it's this, as I promised you. Just as I could integrate out a star, I can reinsert it. I can insert the star here. We use the Star-genvalue equation, and we find that this is equal to E times F. E is a number, it comes out of here. This guy is normalized to 1. So we get that the energy is the expectation value of the Hamiltonian, big deal. As I said before, the normalization matters. Now, we had the star idempotence relationship for the same Wigner function. And this star product is proportional to 1 over h bar times f. F is normalized, so we see that this guy is a finite number. So now this guy, as I said before, has to be a finite number. It's bounded from above. Think of a pillbox that you multiply by itself. It cannot be a delta function. It's softer than a delta function. So classical mechanics is spiky, and it's quantum mechanics that's fuzzy and controlled in size. There is a proof of the uncertainty principle. The corresponding positive definite operator that you use in quantum mechanics is not just the square of an arbitrary function in phase space, but the star square. You can prove that this guy is positive semi-definite, then plug in the corresponding variances and functions of coordinates and momenta, and you could prove on that planet that, in fact, the uncertainty principle works. Oh, this is the theorem that I said before, the backwards and forwards of the standard Star-genvalue equation compliance. But we already talked about this. We don't need to prove it. So this is the takeaway from this part of the talk that, I'm sorry?
Cosmas, before you go to the next part, can I ask a question about the finite dimensional Hilbert space? Let's say you have a spin. So you don't have x's and p's, but just have spin. Let's just one spin.
Yes.
So what happens in that case in this formulation?
It works. Mutatis mutandis. You have to adjust for things. They have worked these things out in finite dimensional spaces, and you have sums instead of integrals. And it's actually, the short answer is it works out. You can't see it right this. We could discuss it later if you wish.
Okay. Okay.
The gentleman, I'm forgetting his name now, who's actually written several papers working it out for finite systems. And it's also been worked on the hypersphere. I'm doing the trivial case of flat phase space. You can huff and puff and work it out in spherical phase space, but let me go on because your question is excellent but recondite, and it has been addressed. Okay, so what I covered so far in the general discussion is that operator multiplication in Hilbert space is in complete isomorphism to star multiplication of C number phase space functions. Okay, now I can understand you'd be yawning because, well, students yawn when you start teaching them quantum mechanics by blasting them with formalism. The question is, give us a trivial example, something that everybody knows about in physics, the linear oscillator that goes boing, 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 boing. What does it look like in this formulation? Because, some students only relax when they see that in quantum mechanics, but they don't relax a lot. Here, they should relax more. Okay, so somebody, let's work in non-dimensionalized, measure everything in optimal units of h bar, m, and frequency. And then the oscillator Hamiltonian is just the radius squared half in phase space. So this is the oscillator Hamiltonian in optimal units. Let's solve the Star-genvalue equation. You remember it had exponential things like that, but life is charmed here. Why? Because whatever it is we Bob shift, as I showed you before, is a finite polynomial. This is very special. It will never be as good. The hydrogen atom is not as good. But here, this is essentially trivial. We Bob shift these guys, and our Star-genvalue equation is a very simple second order partial differential equation. It's a complex one, so it's got a real and an imaginary part. The imaginary part is literally trivial. It tells you that the Star-gen function, is actually a scalar under rotation in phase space. You rotate x's to p's and p's into x's. And so it's a scalar of these variables. So therefore it's a function not of the angle in phase, but the radius or the radius squared, which happens to be the Hamiltonian as well. And so let's define this radial variable to be the square of the radius in phase space with some numbers. The real part of the Star-genvalue equation then collapses to this second order ordinary differential equation. Okay? You make an obvious substitution to get rid of the linear term, and you get this equation, which if you're teaching the hydrogen atom to your students, you recall is Laguerre's equation. Laguerre? What's going on here? We're talking oscillator. Are we in the wrong chapter? We should have seen something with Hermite. Except the convolutions of Hermites are Laguerre's, as people used to know. We didn't know it at the time. But anyway, I'm proud to. So the solutions of this Laguerre's equation are in fact Laguerre polynomials in the one variable, the radial squared variable in phase space, with these eigenvalues. Ho, ho, ho. Now we're in business. You plug them back in, and these are the Star-genvalues of the oscillator, and I put in H because I don't want to be writing the radial variable squared. They're all functions of the Hamiltonian. This is a very special and exceptional thing in this game. The ground state is 1 times the Gaussian in phase space. This is positive semi-definite in phase space. So the ground state is a Gaussian, like ordinary quantum mechanics, like Hilbert Space quantum mechanics, the gold formulation. It's a Gaussian, not in coordinate space, not in momentum space, in phase space. And it's positive semi-definite, and it's star orthogonal to everybody else. Everybody else, the first excited state, the second excited state, has zeros, as you can see from here. At the origin of phase space, this guy is 1, but as you go, well, minus 1, if you multiply it by its prefactor. But then as you increase the radius in phase space, you see that you hit 0, you hit a node, and then it goes negative. And likewise, for the rest of them, none of them is positive semi-definite anymore, as I promised you. Only the ground state is. But you know what they do. Okay. Now, this is an example, for instance, of the third excited state. You can see that it has 3 nodes. It's inside this mode here and inside that mode. They give you a complete orthonormalized resolution of the identity. And you can prove very easily from the properties, from the generating function of Laguerre polynomials, that in fact, they obey this relation, they resolve the identity, they do all the nice things that everybody knows. Hold your breath for a second. It's not as dull as you think.
Can I ask a question?
You can, yes?
Yeah, I'm going back to the Laguerre simple harmonic oscillator connection.
Yeah.
The simple harmonic oscillator only has bound states, but the hydrogen atom can be ionized. So what's the analog of the continuum states?
Well, you find that it's not an eigenvalue equation. You get continuum space. I have to tell you right away, a state, Star-gen state, I have to tell you right away that it's very, very hard to solve the Coulomb potential directly in this formulation.
Okay.
So let's enjoy it while it lasts for the oscillator. So suppose you're the Dirac on that planet, and you realize after Groenewold solved it, which he did in 1946, you realize that, oh, I can expedite this, I can streamline this by noticing that the Hamiltonian is actually, which is the radius in phase space, is actually the star product of 2 functions. They're not operators, they're annihilation and creation functions whose star product with the addition of a half gives you the Hamiltonian that I had before. So x squared plus p squared over 2 is equal to this guy. But these 2 guys star commute just like the Hilbert Space commutation relation of an annihilation of optical phase space operators. Okay. So given that, then you say, oh, all I have to do is to find the star vacuum, the state, the Hilbert, the phase space state that's being annihilated by this, this annihilation function, not operator, star annihilated by this function. So what is the guy that's annihilated by this complex if I Bob shift it? And you immediately found the Gaussian. So you can go backwards. You can do exactly what Dirac would have done. And then you can build all the Star-gen states that now remember, this is like a density matrix. So there are Star-gen values on the left and Star-gen values of the Hamiltonian on the right. And it's exactly like the Fock space states, except, you know, this is the vacuum. These are the left and right Fock space states. But this is this screwed up star space, Fock space, whatever. And they're real. They're left-right symmetric, they're star orthogonal. You can prove star orthogonality in a jiffy like this. They project to themselves like the Star-genvalue equation that I showed, the idempotence equation that I showed you before, and so on and so forth. Okay, in the last 5 minutes, let's look at the time evolution. We already worked all the static stuff. Let's work out the time evolution. The time evolution, it shouldn't be a surprise, is the phase space analog, isomorph of the ordinary quantum mechanical operator propagator. It's the star exponential of the Hamiltonian. The star exponential, of course, is the expansion of the exponential, except wherever you had multiplication in the exponential, now you have a star. So you have star powers of the Hamiltonian. You can solve this equation directly. And guess what? The Moyal's equation, time-dependent equation, is solved identically by this intercalated Wigner function. So just for the oscillator, it turns out that you have something like trajectories. You never have trajectories in quantum mechanics except for the oscillator and a couple of other systems that you can fake. Moyal's equation in this case collapses to an ordinary, just because the Hamiltonians is a polynomial for the oscillator, collapses to very simple rigid rotation equations, and the Heisenberg operators, if you wish, in this for the oscillator are rigid rotators. Okay. This is something, in fact, that Groenewold realized in 1946, that the generic, the absolutely most general Wigner function for the linear harmonic oscillator, its time evolution is dumb rigid rotation. This is much, much better than in the Hilbert Space gold formulation of quantum mechanics. And this is not a coherent state. We'll see it in a second. It's basically a rigid rotation. So you might enjoy appreciating at last why the linear oscillator behaves in such a magical, weird way. This is what it does in phase space. It rigidly rotates in phase space. So this is a generic Wigner function. Real Wigner functions don't have these sharp angles, but I'm giving them sharp angles here to dramatize their projections. You'll see in a second. So the Wigner function for the oscillator goes round and round and round and round. And it need not have an axis of symmetry between x and p, which is the coherent states. In ordinary quantum mechanics, if you dress up your states to be Schrödinger's wave packet states, then you have coherent states that behave like oscillators. If I integrate over P, these guys project in coordinate space to these guys. Now, if you have a coherent state, it looks like a classical oscillator moving back and forth in coordinate space, like boing, 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 boing. Likewise in momentum, if you project it in momentum space. But if your state is not a coordinate state, a coherent state, you have a nightmare. You have something whose projection changes as it moves back and forth. Maybe some type of a center of gravity, moves around like an oscillator, but it changes. Imagine this guy had tentacles, so all kinds of things. You'd find all kinds of freaky behavior in ordinary oscillators, except magically, after one period, you'd be back where you started from. It would look like all the phases conspired and they did amazing things, and they gave you back your original state. But here in phase space, you actually see what's going on. You have a rigid rotation, essentially semiclassical, classical rotation in phase space. That's all you have. So in this respect, this is a charmed system, and it doesn't give you any new results, but at least you can see in this formulation what is really going on with the oscillator. Now, if you add, if you transport this to field theory, and then this is going to be the kinetic term, and you add interaction terms, and they start wiggling on this turntable that you had, and you have something very messy, but at least it gives you some kind of a grip of what this is about. Okay, we're at the end of our trip. This is a penultimate transparency. This is the actual final transparency. I obviously lied to you because everybody lies these ways. This is an election month, or maybe one before the election. I told you it's a different formulation. It's change of coordinates. It's a change of language. It's a very tasteful and pretty change of language that tells you how to go from classical kernels, Weyl symbols, in very many cases, classical observables, not in all. The square of the angular momentum is something slightly different than the classical angular momentum. You plug them into this formula, and by Weyl's recipe, you get an operator that corresponds in a tasteful, unique way to it. And the inverse map for this is the Wigner function that I showed you before. If here you put in the density matrix for one state, the pure state density matrix, you immediately see the expression that I wrote down in my second transparency. And so what you actually are reminded of, in case you hadn't noticed, is that the big lie that you give your students in ordinary canonical quantization in quantum mechanics in the gold formulation, that classical mechanics is C number functions and quantum mechanics is Q number functions and Q number observables and matrices and Hilbert space and all that, is a bit of an exaggeration. Namely, you can describe quantum mechanics perfectly well, both in phase space and Hilbert space. And conversely, you can describe classical mechanics in Hilbert space in a formulation that some people call Koopman von Neumann. The guy that did it best and demarcated the connections between the two is Tony Brackett in Brisbane. But in any case, these are just languages. So phase space and Hilbert space are like Greek and Japanese. You can read the Odyssey in Japanese and the Tale of Genji in Greek, and they wouldn't be terribly different. Maybe you don't want to do it, but there we go. So what I describe is the bridge, the dictionary between the two languages that allows you to get arguably improved insight in selected systems. So all kinds of problems of quantization. How do you quantize the symmetry, say a particle in a sphere and all that, preserving the symmetries? How do you quantize a system with symmetry, preserving these symmetries by going from Poisson brackets to commutators? It's actually easier to account for it by working in this formulation because it's a continuous transition, if you want to, if only in your imagination, between classical mechanics and quantum mechanics. So you compare apples and pears, not apples and oranges. So anyway, this is the end of the trip, and I'm happy to answer any questions.
So Cosmas, is it fair to say that that essentially this phase space formulation is very natural and closely related to phase space path integral formulation? Because in the path integral, essentially the exponent of the I of the action is captured.
This is a good question. I don't have the answer like in one transparency, but yes, you need not go through the Hilbert space formulation to connect to the functional integral. It can be done directly and arguably more elegantly or tastefully. The people that did this sort of thing is Sharan Pankaj, or something like that, somebody at Stony Brook, and Marinov, who has a very nice phase space, I would call it cult of the functional integral, which is extremely tasteful and can convince you that trajectories in quantum mechanics have no meaning, with a few exceptions. It's very, very dangerous to be talking about trajectories in quantum mechanics.
Yeah.
And yes, so there's a full triangle. If you think of three planets, the Hilbert space, the phase space, and the deformation quantization, the phase space planets, they each connect to each other directly, sometimes surprisingly more directly than going through the other guy.
I have to say that
I still don't know how to do the uncertainty principle in the functional integral, but that's just me.
Well, I mean, you can do it, via the.
You can cheat. You can go through the other guy.
But, and then,
sticking within your planet, the confines of your formulation, you have to huff and puff.
But I have to say, just a comment, and then I'll. Leave. I mean, first of all, I enjoyed the colloquium. I think it was similar to what you gave here, I guess, years ago at Virginia Tech, but you added some things. I guess Tom could never make it, so I remember your colloquium. But anyway, thanks. That was very nice. But one thing that I just wanted to comment is that there is this formulation, right, that, well, it goes back to Weyl and Schringer, but I think Aharonov really pushed it for years. That instead of going to a complete basis, let's say, of Hermitian operators in your Hilbert space formulation and the original formulation, you go to a complete set of unitary operators. Mm-hmm. And in that case, when you do that, then you realize that that actually what you're doing is you can actually have a complete set of unitary operators defined in such a way so that you work with commuting unitary operators, essentially generators of translations in, if you want, in your Qs and your Ps.
Vibrating,
And that's essentially just working with the commuting, the commutative subalgebras of Heisenberg algebra, which by Mackey's theorem they're essentially discretized self-dual lattice, which is discretized phase space. And then if you put a Hilbert space on it, you lift it back to the Heisenberg algebra, you get this sort of modular formulation. You can
Yes,
do it
yes,
all
yes,
covariant.
yes.
So the nice thing about this is it's, you know, it's somehow related to this, what you're
Yes.
talking about, but it's in some sense more general because you're getting this wave functions which are modular, and you get the Zach transform, which
It's
is
not more general, they're cousins.
yeah, they're somehow cousins. But okay, so one thing where I see this modular formulation is interesting is when you start thinking about quantum field theory.
Mhm.
And I'm wondering if you have any insights about what happens in the phase space formulation when you start thinking about quantum field theory.
We started thinking about quantum field theory. We did the obvious scalar field in the non-covariant wave functional formulation. And for free field theory, everything works like a charm. Why? Because it's an assembly of oscillators. You start trying to find non-trivial things for interactions, and we're nowhere close to anything usable or practical. I neglected to mention in my talk today that you can do ordinary perturbation theory in this formulation very analogously, very similarly and elegantly to the Hilbert Space formulation. It actually works out like a charm. And we have a chapter of this in our book. For field theory, you can get started, you can start the translation, but then it starts getting very tricky because you really have to work with the, you know, it's not Jakiv, it's the wave functional formulation of field theory, which is.
Well, I guess it's, and you lose covariance and things like that.
But going back to Weyl, let me start ranting. This is how we were led to it with my collaborator, David Fairley, back in the 90s, actually. It turned out that the Weyl relations for quantum mechanics around the clock, a finite number of coordinate states, and the finite clock and shift matrices that represent these operators that were constructed by the great Sylvester in the 19th century. When you actually look at the braiding relations and their exponentials, we discovered with David Fairley that actually what you get is a star product, which he knew about from 1964. There were the discrete versions of the star product. There is a very tasteful discrete version of the Moyal brackets, and it's a matrix. And in fact, they're the basis of the formulation of Voerdas and another gentleman that I feel terribly guilty of not remembering his name. I think it's a Dutch name in Maryland someplace. Who's done the entire enterprise for finite dimensional Hilbert spaces for quantum mechanics on the clock.
Okay. Anyway, okay. So that was nice. I mean, another thing about this modular formulation is that it gives an insight into non-locality. So I don't know if you can say anything about entanglement, right, and things like that.
Wigner functions, certainly I can't say anything personally, but Wigner functions are really a weapon of choice for a certain subsection of the quantum computing community that likes to visualize entanglement. Yeah. So you can do EPR, and even Bell did his inequalities in phase space, but it was, you had to know I had to know the answer to understand it in phase space. And I didn't want to come close to this. But yes, there's a cottage industry of Bell inequalities and entanglement in phase space.
Yeah, thank you. Thanks, Cosmas.
Cosmas, can I ask you? I'll try to keep this question short.
Yeah.
If you can have negative probabilities anywhere,
yeah,
can you equally have probabilities that are bigger than one?
Yes, because it's a probability density. You can never have, remember the F is a probability density. So yeah, it has all kinds of fluctuations and all that. It's normalized to 1. So the probability itself is the integral, which is 1, just like the probability in quantum mechanics is 1. The value of the Wigner function can be negative, it can be positive, but as I showed in my third transparency or so, it's bounded above. So it can be bigger than 1, of course, but it's 2 over h or something like that.
Okay,
And it can't be any higher. In classical mechanics, if you recall, your probability is a delta function. If you're a particle that's at a given point in phase space, you're a delta function whose integral is 1, but you're a delta function. No such luck in quantum mechanics. You're fuzzy, you're a marshmallow, a limited blobby marshmallow, never spiky.
okay. That's all.
Okay. If I may make some
Yeah.
comments. First of all, we have to thank Tom Kirchwright for coming up with a clock that's showing Central Time, just for Cosmas's benefit. The other comments I have, I think that this whole approach, which is fine, will fail in the situation where you're working in the quantum mechanical Hilbert space does not have all states with positive norm. Namely, if you have 0 norm states, it looks to me like they would be outside of this approach.
Yeah.
The only time you get 0 norm states, I mean, ignoring gauge theories with artifacts, is if you have a Hamiltonian that's not diagonalizable.
Yeah.
And
I'll
so
defer to the chairman.
I think there are things in quantum mechanics that don't translate into classical.
Yeah, I know what you're doing. You're drifting towards PT quantum mechanics.
Well, no, that was how I knew about it. But
And Tom has dabbled in it in phase space and has written 1, 2, 3, whatever papers, Van Kortrijk, you name it. And you'd best talk to them because even though I'm a co-author on our little booklet here that has a chapter on PT quantum mechanics, I cannot profess working expertise in it.
no, I mean, what you're doing, making the transition from a Hermitian Hamiltonian to a Hamiltonian with an antilinear symmetry, I think is straightforward because nothing really depends on the Hamiltonian being Hermitian. However, what is separate is whether non-Hermitian Hamiltonians allow you to have an incomplete basis of states.
Yes, yeah. I don't know. These are deep fundamental questions, and there is a gaggle of mathematicians working on everything under the sun, but I don't want to animadvert our mathematical friends. They're trying to shoehorn everything that they see in this formulation in the language of negative measures. And I can steer you to papers that seem to be talking about things you're talking about, but they have a long history of focusing on things that are attractive to them and not things that are natural or attractive to physics. So it's translation.
I hate to cut off this discussion, but we've just been reminded by our chairman at the University of Miami that we have a faculty meeting.
Okay.
And I thought you meant they weren't paying for a Zoom for more than an hour and a quarter.
They're not. Yeah, that's probably true too. Yes.
Okay.
But anyway, if you have additional questions, by all means,
Submit them
email,
by email.
or
I'm
Zoom.
here.
Do a personal Zoom with Cosmas. But the official recording of this Zoom session is coming to a conclusion. And so let's thank our speaker. And I thank everyone for participating in this talk, especially people outside the university. So thank you, guys. Thank you, speaker.
Okay,
We'll see the rest of you at a
nice having been there.
Yeah, the weather's nice here. Okay, so
Yeah,
bye, guys.
okay.